Let's talk about associations between variables and about predictions from one variable to another. We start by talking about bivariate associations, which are relationships between two variables. Let's call them x and y. A positive association means that as variable x increases, variable y tends to increase as well. So an example is height and weight. As we grow taller, our weight tends to increase. Another example is income and education. The more income we have, the more education we can afford, and the more education we have, the more income we're likely to make. A negative association is one in which, as one variable, x, increases, the other variable, y, tends to decrease. So examples include the relationship between activity level and depression. The more active we are, the less depressed we're likely to be. The more depressed we are, the less active we're likely to be. Another example is the relationship between alcohol consumption and dexterity, or response time. And a third example is the relationship between education and fertility, or the number of children that women have. So here's some examples. Here's a positive association showing on the horizontal axis, called the x-axis, rates of child mortality in different countries. And on the horizontal axis, or the y-axis, we see fertility rates, or the average number of children per woman. And you see here the positive relationship means that in countries with higher child mortality rates, there is a larger fertility rate. Women tend to have more children in countries with high child mortality rates. Here's a negative association. In this case, it's between, on the horizontal axis, the average years of schooling for women of reproductive age, and another measure of fertility, here on the vertical axis, the number of live births per woman. And you see that in countries where women receive, on average, more schooling, they also tend to have fewer children. So that's an example of a negative association. What are some other examples of positive and negative associations from the questions or hypotheses that you're working on? Correlation and causation are two very different ideas. So associations or correlations between variables do not necessarily establish causality. There are several reasons for this. One is that the direction of causality in a relationship is often unclear. It's not clear which variable is the cause and which is the effect. The example I gave you of the relationship between income and education is a good one. So we know that as income increases, education tends to increase, but which is the cause and which is the effect? Could go either way. And other variables may account for this observed association. So there could be other explanations for this relationship that we observe. Some relationships are called spurious. In a spurious correlation, two events are inferred to be related, despite the fact that they have no logical connection to each other. Here's an example. Shoe size, let's call it X, is positively correlated with math performance, call it Y, meaning that people with larger feet tend to do better at math than people with small feet. But there is a third variable that completely explains this relationship. What is it? It's age. The older we get, the better we tend to be at math up to a certain point. So this is an example of confounding. Confounding suggests that there is an association where none exists, or it may be masking a true relationship. Can you think of another example of a confounding factor that explains an apparent relationship between some exposure and some outcome? Well, here's an example. Hormone replacement therapy is associated with the prevention of cardiovascular disease. But there is a confounding factor here. What is it? It's socioeconomic status, in particular the education components of socioeconomic status. Why? It's because women of higher socioeconomic status are more likely to receive hormone replacement therapy than women of lower socioeconomic status. And quite apart from the receipt of HRT, women of higher socioeconomic status are less likely to get cardiovascular disease than women of lower socioeconomic status. We're also interested in associations between multiple variables. And so we use multivariate analyses to assess relationships between multiple variables, more than two. Often we're interested in looking at a relationship between our focal variables x and y, controlling for influences of other variables. We're also interested in multiple associations between variables. So here we can think of multiple predictors of some outcome like job performance. So in this model, researchers think that salary, job satisfaction, and years of employment all affect job performance. And job performance might affect these things as well. So we're interested in more complex networks of association here. Here's an example of an associational study looking at positive relationships between self-reported childhood abuse and prescription opioid use in early adulthood. This study controls for the influence of other variables, including sex, age, race, ethnicity, and welfare received, to see if the reported relationships between childhood abuse and opioid use are stand up after controlling for those influences. In this study, they do. But the study is limited in some ways. It uses cross-sectional data collected at one point in time, and it relies on self-reports of both childhood abuse and current opioid use. We'll come back to this study in a minute. We can visualize associations between continuous variables or interval level variables using scatter plots. So here on the left, you see a data sheet in which each case, identified by first name, provides data on two continuous or interval level variables, x and y. And the scatter plot, the grid on the right, shows you each case as a data point, and we have plotted each case at the intersection of its values on the x-axis, the horizontal axis, and its values on the y-axis, the vertical axis. So you can find Mary's data at the intersection of 3 on the x-axis and 4 on the y-axis. All of the cases in this little hypothetical study are represented here. Then we can draw a line, it's called a line of best fit, through the data to show an overall trend, a pattern of association between x and y. So here's a scatter plot now with a trend line. So this scatter plot represents correlations. And correlations can range from +1 to -1. +1 is a perfect positive correlation in which every increase in x is accompanied by an increase in y. That positive perfect correlation doesn't happen in our world, but high positive correlations like 0.9 are very strong trends. And then here you see a positive correlation of 0.5. I actually don't think that's a low correlation. That's a pretty robust correlation in the social sciences. A correlation of 0 is really no correlation at all. The values don't seem linked. A low negative correlation is a trend toward a negative correlation. This could be important in the social sciences. A high negative correlation approaches the value of -1, and a perfect negative correlation is -1. Again, very rare in our experience. So how do we interpret these correlations? The correlation coefficient is represented often with a small case letter r. And Jacob Cohen gave us some guidelines that are somewhat arbitrary but still widely used for interpreting correlation coefficients. In Cohen's guidelines, a correlation of 0.1 is small, a correlation of 0.25 is medium, and a correlation of 0.4 is large. We also can produce correlations in matrices showing pairwise relationships between multiple variables. So here, each entry in this correlation matrix is a correlation coefficient, and it represents the relationship or correlation between two variables in the grid. So in column 1, the first number that you see at the top, 0.96, represents the correlation between variable 1, which is working memory, and variable 2, which is executive function. These two variables are very highly correlated. So looking at this matrix, which correlations are positive and which are negative? That's pretty easy to see because of the presence or absence of the negative sign. Which correlations are small, that is less than 0.1? Which correlations are medium, around 0.25? And which correlations are large, larger than 0.4? There are several types of bivariate associations, depending on the kind of data that we're working with. We use correlations to look at associations between two continuous or interval or ratio level variables. We use contingency tables with either odds ratios or risk ratios to examine associations between two dichotomous variables. And we use standardized mean differences to look at a dichotomous predictor in relation to a continuous criterion variable. Now I'm going to give you examples of all of these, but first I'll say that there are other metrics that we can use to examine bivariate associations. I've named some of them here. You don't need to worry about them, but do understand that there are other measures of bivariate associations. These three, I'll call them families of measures, are the most commonly used in social work and social sciences. So odds ratios and risk ratios are used to assess the relationship between two dichotomous variables based on frequencies or counts of observations in a 2x2 contingency table. So here is a 2x2 contingency table. It has two variables, each with two categories. So one variable is outcome, and its categories are success or failure. The other variable is the kind of treatment that the individual received, and its values or treatment or control. This is the basic setup for calculating both odds ratios and risk ratios. Now an odds ratio, or R, uses odds. Odds are something that are very familiar to gamblers, but may not be intuitively obvious to you. It certainly is not intuitively obvious to me. The odds are the chance of an event. You could focus on success or you could focus on failure, but the chance of an event of your choice over the chance that that event will not happen. So the odds of success for treatment are A over B. The odds of success for the control group are C over D. And then the odds ratio is the ratio of these two ratios. So A over B divided by C over D. Now the math is not hard, and I just plugged in some numbers to show you how this works. So the odds of success for the treatment cases, we have 6 successes and 4 failures. So the odds of success in that group are 6 divided by 4, or 1.5. The odds of success for control cases are 5 over 5, or 1. The odds ratio is the ratio of these two ratios, or 1.5 divided by 1. So the odds ratio is 1.5. I'll explain what this means in a minute, but let's just understand how we're calculating it first. So do this calculation yourself. What are the odds of failure for the treatment group? What are the odds of failure for the control group? Now calculate the odds ratio for failure. What did you get? Let's now look at risk ratios. So risks are a little easier for me to think about anyway. Risks are the chance of an event, either success or failure in this case, the chance that will happen overall. So the risk of success for the treatment group is A divided by the total of cases in that group, A plus B. The risk of success for the control group is C, the number of successes, divided by the number of total cases in that group, which is C plus D. And then the risk ratio is the ratio of these two ratios. Now that looks confusing, but actually it's a little easier to work with real numbers. So again, we'll plug in some real numbers, same numbers we had before. The risk of success for treatment cases is 6 out of 10, 0.6, probability of 0.6 of success, or you could say a 60% likelihood of success. The risk of success in the control group is 5 divided by 10, or 0.5. And the risk ratio is the ratio of these two ratios, 0.6 divided by 0.5, or 1.2. So this tells us that the risk of success is 20% higher in the treatment group than it is in the control group. It's a little more straightforward in terms of interpretation. So on your own, calculate the risk of failure. What's the risk of failure for the treatment group? What's the risk of failure for the control group? And what's the risk ratio? Here's a summary of everything I've said about the odds ratio and risk ratio so far. There's nothing new on the slide. I just thought it might be helpful to you to have it all in one place to see it. And now let's work on interpretation. Interpretation of odds ratio. The odds ratio ranges from near zero to infinity. An odds ratio of 1 means that the odds are the same, identical, in both groups. An odds ratio greater than 1 means the odds are highest in the first group. So if you're comparing treatment to control, an odds ratio greater than 1 means the treatment group had greater odds of the event than the control group. An odds ratio from 0 to 1, meaning an odds ratio lower than 1, means that the odds are lower in the first group than in the second group. This is difficult to interpret because it doesn't map directly onto the probability that something will happen. The risk ratio does that, and so it's more straightforward. The risk ratio also ranges from near zero to infinity, and as with the odds ratio, a risk ratio of 1 means that the risk is the same, identical in both groups. A risk ratio greater than 1 also means that there's a higher risk of the event in the first group. But again, this was easier to interpret. So a risk ratio of 1.2 means there's a 20% greater chance of that event in the first group. A risk ratio that is lower than 1 means that there's a lower risk in the first group. So a risk ratio of 0.8 means there's a 20% lower chance in the first group. So I hope that you calculated that the risk of failure in the treatment group is 0.8, 20% lower. But we do see odds ratios very, very often in the social science literature, and it's important to know how to interpret them. So back to our study by Anna Austin and her colleagues of associations between childhood abuse and prescription opioid use. Here, researchers present the results of their analysis in terms of odds ratios. So here you see on the left side 4 outcomes, and the second column is the unadjusted odds ratio, just showing the relationship between a type of childhood abuse and current or recent prescription opioid use. And then the next columns moving toward the right are confidence intervals for that odds ratio. Moving further to the right, we see an adjusted odds ratio where the researchers are factoring in the variables of sex, age, race, ethnicity, and parents' receipt of public assistance. And then finally at the far right, we have confidence intervals for the adjusted odds ratio. So my first question to you is, are these associations positive or negative? Remember that an odds ratio of 1 means the odds are the same in both groups. And these unadjusted and adjusted odds ratios are all greater than 1. meaning that respondents that with some kind of a childhood emotional, physical, sexual, or any abuse are more likely to have recently used prescription opioids than respondents without childhood abuse. That's what they mean. What happens when the odds ratios are adjusted for the influence of other variables? Do they get stronger or weaker? So here compare the unadjusted odds ratio for childhood emotional abuse, 1.53, with the adjusted odds ratio of 1.57. It gets stronger, greater than 1. Most of these relationships do get stronger with the exception of childhood sexual abuse. That's a little weaker, moving from 1.17 to 1.14 after we adjust for the influence of other variables. But I think what's important here is that the adjustment for these other variables doesn't make much difference. So these relationships really do hold up even when adjusted for these other factors. Now let's take a look at the standardized mean difference. This is a measure that's used when we're interested in comparing two groups on a continuous outcome variable. So we have a dichotomous predictor and a continuous criterion or outcome variable. Examples could be comparisons of income for high school graduates versus dropouts, or comparisons of test scores for treatment and control groups. The standardized mean difference is the difference between the means of the two groups, the mean on the outcome measures, divided by their pooled or joint standard deviation. So we're expressing differences between the groups in terms of outcomes in standard deviation units. The interpretation of the standardized mean difference isn't immediately obvious, so I often refer to this graphic representation to remind myself what it means. A standardized mean difference of 0 means that the outcome distributions for the treatment and control groups are the same. There's no difference. A standardized mean difference of 0.4 means that the averages for these groups are different by about 0.4 standard deviations. So in this case, the treatment group does better. 0.4 is a positive difference. So the whole group's average is shifted up toward the right on the scale. If the result was negative, the standardized mean difference would be a negative 0.4, and you'd see the treatment group distribution shifted to the left toward a negative number. In the final picture at the bottom, you see a difference of standardized mean difference of 0.85, meaning the group averages differ by about 0.85 standard deviations, almost a full standard deviation. That's a huge difference. When we get standardized mean differences of 0.4, that's usually an effect that's worth paying attention to. So these are all effect sizes, these measures that we've been talking about. And an effect size is any measure of the direction, that is the positive or negative direction, and magnitude, size, of a relationship between variables. The effect size is more important in terms of interpretation than statistical significance. And there are three main families of effect size. These are the families we've been talking about: correlations, odds ratios and risk ratios, and standardized mean differences. Here's a guide for interpreting these effect sizes, again following Cohen's standards. So here we have our three families of effect size metrics or measures with Cohen's guidelines. So for odds ratios, remember that an odds ratio of 1 means that the odds are the same in both groups. An odds ratio of 1.5 is a small effect. 2.5 is a medium effect, 4.3 is a large effect. Standardized mean difference, 0.2 is a small effect, 0.5 is a medium effect, 0.8 a large effect. And correlations, as I said before, 0.1 is a small difference, 0.25 is a medium effect, 0.4 large effect. So we use effect sizes a lot to understand research results and also to synthesize results across multiple studies. So effect sizes can provide us with common metrics for looking at results across studies in meta-analysis. Let's move now to talking about prediction, how you would predict one variable from another. So this requires evidence of association or correlation and something in addition, time order. Here, to show that one variable predicts another, the predictor has to come before the criterion, outcome variable. This seems rather obvious, but it does impose a new requirement. So x has to come before y, and we have to show that y did not precede x. So we discussed this when talking about cross-sectional and longitudinal studies. And when we said that in order to predict one thing from another, we can use case control studies, which compare cases with and without an outcome of interest, and are looking back, often retrospectively, for differences in prior to exposure to risk or protective factors. But because that's retrospective, a better way to do this is to use a cohort study that begins with data on exposure to a risk or protective factor and examines future likelihood of outcomes of interest prospectively. So in terms of critical appraisal of studies of correlations, we want to look at several things. In addition to criteria that we've talked about before for interpreting studies of constructs and rates, now we also want to ask whether associations were analyzed in appropriate ways given the level of measurement of variables of interest in the study, that is, whether the variables were dichotomous or continuous. We want to ask what is the effect size and is it meaningful? And we want to ask whether other variables could account for the association, and if so, which ones? So these are key questions to ask in critically appraising studies of correlations. Now, in critically appraising studies of predictions, we'll add a few more questions. Has time order been clearly established? Are we sure that the predictor occurs before the criterion variable? Is reverse time order possible? And again, could other variables count for the relationship between the predictor and the criterion variable?